Hi, and welcome to another exciting edition of 3D game development. My name is Nate Nestler, and this is Fiber Studios. Now, last time we left off with part 1 of deferred shading with MRT or multiple render targets. But now, and also deferred lighting too, actually. But now we're going to continue on here, starting off with textures here. So, going to the textures, we're going to do a color texture here. And that's going to be this texture here. It's going to appear on the screen. And we're all familiar with this. It's the same old thing that we've been doing. It's regular part of the regular pipeline, standard shader stuff as far as color textures go. So texture here, color texture, is the name of it. Open less than sign here. String resource name equals in quotes default underscore color dot DDS close quotes semicolon, and then string UI name equals in quotes diffuse texture close quotes semicolon, and then string resource type equals in quotes 2D close quotes semicolon close greater than sign semicolon. Alright, sampler 2D color sampler equals sampler underscore state here, open curly brace here, texture equals in parentheses, so in greater than less than signs control color texture match with this one here, of course. Close greater than sign semicolon here. Min filter equals linear mipmap linear semicolon. Mag filter equals linear semicolon, and then wrap s here equals repeat semicolon. Wrap t equals repeat semicolon. Close your curly brace semicolon, and standard is what we're used to doing here. Okay, let me scroll it down just a little bit here, and then I'll continue on with the next one. Now you gotta realize the next one here is going to the G buffer. This is an actual file texture on the computer, whereas this here is not. This is actually going to be generated at runtime for the shaders, and we're actually generating this texture on the fly. And there's a couple of things about this. We already done this a bit before, but just rehashing this. But we're going to do this 3 times at once, so we're actually can generate 3 of these images, and then we're going to kick one out to the stencil buffer for the depth. So that's kind of important because well, basically it's how we're going to get around with doing our real-time rendering to the G buffer. And so we're going to do our deferred shading because we have to render everything to pretty much to G buffer for the most part, except for the depth one. Alright, so we have our texture here, and I called it deferred color texture because that's what makes sense. And then colon here is going to be render color target, and that's what's going to make it go to the G buffer here inside of FX Composer 2.5. Now if I open up with a less than sign here, and say float to here, viewport ratio equals curly brace here 1.0 comma 1.0 close curly brace semicolon, and that's going to be the ratio here. And then we're going to do int mip levels equals 1 semicolon. That's because we can actually generate mip maps with this, and we can have multiple levels of mip maps. If you refer back to when I went over mip maps with DX1 through DX5, I went over how mip maps work and what they look like as you're going off into the distance, and how they can actually degrade on purpose as an optimization method inside of the 3D hardware, and it swaps out the textures that go through different levels of detail, but it has to be a power of 2 is the key to that. In our case, we're only doing a MIP level of 1 because we don't care about the level of detail aspect of this. We're generating this for the screen, and we're not going to have it go different depth levels. So if we did have it go different depth levels, we could set that up in the MIP levels, but unfortunately it's not going to work for what we're doing. So we're just going to do MIP levels 1, so actually means less work for us. And that's that as far as that goes. The string format here is to make this a 16-bit image here for each channel. So this is high detail for the color. Now you could do it lower detail at 8 bits for each one, but we're doing it at high detail right now. So it's alpha, 16-bit for alpha, 16-bit for blue, 16-bit for green, and 16-bit for red. So this is pretty detailed. It's going to have a lot of color information in it. String UI name, previously we were using A8, B8, G8, R8, and that'd be 8 bits for those. So 16-bit, and here we're doing 16-bit. Our string here, UI name equals, here in this case, deferred color texture, and I need to move that over one. And then that's going to be what we're going to use for our, well, for the name of this texture, actually. We could set it up to where it doesn't appear in this setup here, but that's not what I have set up currently. But we could set that up to where it doesn't show up in the annotation, up in the interface over here. It's up to you whether you want it to or not. But feel free. We've set our UI widgets here before to none. If you look up here, right here where it says UI widget none, I believe that should also work for annotation, if I'm not mistaken. So essentially, if I came in here to this part here and I typed in none, like so, save, compile, yeah, it disappears. So if you want to get rid of these, just pop in none here in your UI widget to make them disappear. So they're being computed, but they're not being seen on the interface, which is probably ideal. They'll still appear in the textures being generated, they're just not going to appear over here where people can mess with them. So, you know, it's totally up to you what you want to do. So we're going to move forward here. Sorry, I hope you're done copying this part down. We're going to go, if you're not, just pause it. So we're going to continue on here. So once you code one of these, feel free to copy and paste, because it's going to be the same thing over and over again, except we're just going to change out the name here, really, and the title here. As far as that goes, everything else is the same. Nothing. They're all going to the render color target, so basically G buffer. So that's not about to change. Of course, if you're copying and pasting this, you don't even have to type in none again for these other ones here to make another one disappear. So this is all we're doing here. We're going to say deferred normal texture here. So deferred normal texture here, going to your render color target, and then open less than sign here, float to viewport ratio here equals open curly brace here 1.0 comma 1.0 close curly brace semicolon, int mip levels here equals 1 semicolon, string format equals in quotes A16 B16 G16 R16 close quotes semicolon, string UI widgets UI name equals in quotes here deferred color texture close quotes semicolon, string UI widget equals none in quotes here close quotes semicolon. So that's going to be your deferred color. You can do the same thing here for the normal. So change the color to normal here, and same thing goes for when you're applying it here in the name, change that to normal. And then for the sampler, same idea, copy and paste the sampler. I should go over the sampler, shouldn't I? Sampler 2D here, deferred color sampler equals sampler underscore state, texture equals in less than sign here, deferred color texture close greater than sign semicolon. That was the same name of the texture we had up before that's being generated. Mag filter equals linear semicolon, min filter equals linear, mip filter equals point semicolon, and wrap s equals clamp to edge. That's important because we're going to the edge of the screen. Wrap t equals to clamp to edge, going to the top edges of the screen, close curly brace semicolon, and there is our actual shader there. Very cool. Okay, and that covers your deferred color sampler. Texture deferred normal texture colon render color target here, open less than sign, float to viewport ratio. Oh, it's the same thing. Just replace deferred normal texture here with just deferred. Yeah, switch in normal over here, switch in normal here, and then switch in. Yeah, that's pretty much it. Normal here, so on and so forth. That's it. It's the same thing over and over again. Same thing for view. Copy and paste again. Here we go. Swap in view now. Swap in view over here. We already have our none in there. Very nice. Very nice indeed. And then swap in what? View here and view here. For your copy and paste. Everything else identical. It's the same. It doesn't change. Alright. Moving on down. And we're getting to our depth buffer. I'm going to pop in none. Now this one's slightly different, guys. Feel free to copy and paste to save a little time here and effort. There, I made all the others disappear. Now the only one we can change is actually the diffuse texture. These are still generated, no problem, but this is the only one that's actually getting where you can change it in the scene. It'll update for all the models. But anyhow, all that aside, okay, so texture here is depth buffer texture colon render depth stencil target. And open less than sign here, float to viewport ratio equals curly brace 1.0 comma 1.0 close curly brace semicolon, string format equals in quotes D24 S8 close quotes semicolon, string UI name equals in quotes depth space buffer space texture close quotes semicolon, and then string UI widget equals quotes, none, close quotes, semicolon, close greater than sign, semicolon, sampler 2D, def buffer sampler equals sampler underscore state here, open curly brace here, texture equals and less than sign here, def buffer texture, close greater than sign, close greater than sign, semicolon, mag filter equals linear, semicolon, min filter equals linear, semicolon, mip filter equals point, semicolon, wrap S equals clamp to edge, semicolon, wrap T equals clamp to edge, semicolon, close curly brace, semicolon, and then that finishes up this one here for our def buffer. Okay. And this gives us our in and out. So you can see this is pretty much all the same down here. It's just a matter of changing the part from above to def buffer texture. This is mostly the same in here too. But you are doing to render stencil, render depth stencil target, and this is going to be def buffer texture instead. And def buffer texture there too. Okay. In and out parameters. Alright. Actually, ideally here, and I didn't do this earlier. Yeah. Okay, let me see if I can't get away with it real quick. Sorry. I have my own conversation with myself here, I guess. And alright, so VSN, I think I'm doing a screen here. Alright, ideally, let me double check it and test it and make sure it works fine, but I'm pretty sure it will. It's just I prefer this over what I've been doing, just in order to reduce variables being passed and another pass that's not needed, and you can get more resources on the card than what's necessary. I don't know. Right, so VSN here could have been instead that one there for our screen instead of our main. Now, our main needs to be that, but not for this necessarily. And that's why I thought it works fine. Okay, so yeah, that will work, and that'll be nicer than doing the other one. Okay, so what did I just do? Okay, sorry, I caught this earlier and I wanted to fix it and then forgot about it, and then as soon as I saw it, I was like, oh yeah, I want to fix that. Okay, so basically, you know, I didn't need all this information to go into the screen because we're talking about the quad here. It's aligned to the screen, and that's determining the actual screen size of the image texture that's being generated. And so we don't need all these extra properties here. We do need that in our main, but we do not need that in our screen one for the second pass. So I simply eliminate them because this has to do with the actual quad texture, 4 points here, that's being perfectly aligned to the screen, and textures are being rendered to that. So, you know, it's not really necessary to have normals and tangent binormals because we'll never use them. So might as well reduce system resources and put it down to just this here for that other pass. And that's what I was doing just now. In this case, this is going into our main one, which is going to be what initially does our Phong type shader. It's not fully computed until we do the second pass though. So we're going to do our struct here, VSN here, open curly brace, float 3 position colon position semicolon, float 2 UV colon text chord 0 semicolon, float 4 normal colon normal semicolon, float 4 tangent colon tangent 0 semicolon, float 4 binormal colon binormal 0 semicolon, close curly brace semicolon. Alright, struct here, VS screen in, close, open curly brace here, float 3 position colon position semicolon, float 2 UV colon text core 0 semicolon, open curly brace semicolon, and there we go. Alright, and that does it for our passing in our variables for our screen end, makes up our screen quad, and then the other one here is dealing with our positions for the points on our models here. Say plural here for models because we're talking about dealing with the different models here. UVs on them, the normals on them, the tangents on them, and the binormals. In this case, we're doing tangent 0 and binormal 0 because you can have more than one happening there. Alright, so struct here, VS out, open curly brace, and then we're going to have a float 4, position colon position semicolon, and then a float 2, UV colon text chord 0. And this is for VS out, of course. And then float 3, you should be very familiar with this. LWN, which is our light direction vector in world space normalize, colon, so let's go into text chord 1, semicolon, which remember we can't pass this any other way. Float 3 here, normal and world space coordinates normalized, and that's going into colon text chord 2, semicolon, and then float 3 again here for our view directional vector, which is our view vector world space coordinates normalized, and that'll be colon text chord 3, semicolon, and then we're going to do our float 3 TWN, because this is what? This is our tangent one, right? So colon text chord 4 here, semicolon. This is our tangent vector in world space coordinates. It's been normalized. And then float 3 here is going to be our binormal world space coordinates, binormal world space coordinates normalize colon text chord 5, semicolon. And then we're going to open a curly brace, closing curly brace, semicolon, and this is going to set our VS out. We need to output all this information because we need to pass it in to actually have it output these textures that we can then handle in another pass. So it's really important because we got to pass all this out to go into the PS shader so we can generate these images, and the PS shader is what's going to actually generate the images. So this is rather important actually. Same thing for, we also have to do a VS screen out for outputting from the actual quad aligned screen here to actually be outputted so it can be rendered on the surface. So what we need with that one, we need the position points of the quad, and we need the UVs. So we're just kind of doing a pass through here. We get our positions and our UVs, and we need to pass it through out, so that way it can be accessed by the pixel shader, so it can do something with it. In this case, actually display those combined images here in the previous pass, combine them together into a single picture that's going to be displayed eventually in a frame buffer. So that's why we're going to be handling this here. So it's just kind of a pass through here for this float 4 position colon position semicolon, and then we're doing a float 2 UV colon text chord 0 semicolon close curly brace semicolon, and that's kind of to be expected there. Alright, so we already talked about our FS out, and we definitely need to do that. So struct your FS out, open curly brace here, float 4 color colon color semicolon close curly brace semicolon. Alright. So this gives us our color out as you expect. It goes to our frame buffer that will eventually be displayed on the screen. Okay. So that covers all those structs. Let's move on down. Now we're doing pretty good actually. Let's get into our vertex texture. Shader. Sorry, not texture, shader. So our vertex shader. Alright. So some of this is going to require more explanation here pretty soon. So here's our VS screen out, screen VS here, open parentheses, VS screen in, close parentheses, open curly brace, VS screen out, out, semicolon. This is all should make sense. So basically what we're saying, we're going to pass in what? Our positions, our UVs, we're going to output them, our positions and our UVs. That's what we're doing. That's all there is to it. Nothing more than that, really. So we're saying out.position equals what? Float 4 here, open parentheses, take our non-homogeneous coordinate system here for a position in object space and return the homogeneous one. So in.position.xyz, comma, 1, close parentheses, semicolon, out.uv equals in.uv.xy, semicolon, return out, semicolon, close curly brace, vs out, main vs, open parentheses, vs in, space in, close parentheses, open curly brace, VS out, space out, semicolon. Alright, so here we have our VS out, what we have going on here. Alright, so we have float 4 here, PO, which is our position of our points in object space, right? Equals float 4 here, open parentheses, in.position.xyz, comma, 1, close parentheses, semicolon, and this is what? This is going to be given our positions and homogeneous coordinate system. Great, but we also need it in world space coordinates here for position. Why? Because we're dealing with world space coordinates for this overall thing, so everything can communicate together on the same coordinate system. Very important. So we're going to do a float 3 here, P for our point position, and world space for the W for the world. So it's going to be our different points on our models, right? Multiply it times the world matrix, and we're going to multiply that by what? Our PO, or our point position in object space. So we're going to convert this from object space to world space. So world XF here, close parentheses, dot xyz, semicolon, and then this gets across the idea that this is a float 3 and we're passing back 3 values. And in this case, it's actually important because these are float 4s at this point, so we do need to convert this from a float 3 to a float 4. Whereas it's not important here because it is just a float 2 here, so it's just for clarity that that is 2 values there. We are not actually doing anything as far as manipulation goes, as far as that goes. They are already in the correct format. We're just making it explicit, more or less. Out dot normal here in world space coordinates normalized. Equals normalize here, open parentheses, mole here, open parentheses, world ITXF here is world inverse transposed matrix, and we're multiplying that times our IN dot normal here, close parentheses, XYZ, close parentheses, semicolon. Alright, so this is going to get our normals and our inverse transpose world matrix, which is to say that yes, the object can be non-uniformly scaled and it will not screw up the normals. So that's important. That's why we're doing that world inverse transpose, right? And we're normalizing that because we can end up with something greater than a magnitude of 1. So we need to get it down to just a magnitude of 1. So we have a unit vector, as it's called, for our normalized. So that's what we're doing, the normalized, normal, and world space coordinates. And we're outputting that. All right. So out.vwn, which is our view vector in world space coordinates normalized, equals normalized, open parentheses, float 3 here, open parentheses, view ix here, f, open bracket, 0, close bracket, dot w, comma, view itx, which is to say the view vector, well, actually, sorry, I take that back. This is the view matrix where we're accessing what? Transpose x, translate x. It is translate x, translate y, and translate z. I've already gone over this like way too many times. I'm not going over it again. Look back at several videos back. I did it in umpteen videos, so you don't have to try that hard to find one that I've covered it several times. Minus position in world space coordinates, and that subtracts from that semicolon there. Alrighty. Then we have out.twn, or tangent space world coordinate system normalize, equals, we're going to do that now. We're going to make our tangents normalize. So we're going to put in world space coordinates, right? So we're doing a world inverse transpose, right? And we're multiplying it. Sorry, Cat was helping out with the scrolling of the mouse. World inverse transpose here, and in here, tangent. So we're making our tangent in world space coordinates, and we're normalizing that. And it becomes a world space normalized tangent here. So our tangents in that case. Out.bwn, which is binormal here. So world space coordinates for our binormals. So now our binormals will be in object space, will be in world space. And then we're going to do what? We're going to normalize them. So that way they're just directional vectors and unit vectors, shall we say, and no actual magnitude. Okay, awesome. So that's going to be our BWN there for our out. All right. So out.uv equals in.uv.xy semicolon. Now again, this xy is not required. Out.position equals mole here, open parentheses here, world view projection, comma PO, close parentheses, semicolon. All right, and this is going to move our position into what? World space. World view, sorry, coordinate projection matrix. So it's the model view matrix. And yeah, sorry, Cat's made some things, play toys on the desk. All right, so out dot position equals mole here, open parentheses, world view projection matrix that we're so familiar with for our model view matrix. Okay. Comma, and our PO for our point position object space, close parentheses, semicolon. And again, this does our manipulation, skewing, and perspective distortion of our model. So that way we have a perspective distortion of your camera. And we're just modifying those points positions based on that matrix for modifying the different points accordingly. So there we are. Return out, semicolon, close curly brace. Awesome. Okay. Okay, so we're going to do our pixel fragment shader now. And this gets us into a subject of what? Float 3 here, vector 2, texture, vector 2 texture here, open parentheses, float 3, vec here, close parentheses, open curly brace, return. Now, where have we seen this algorithm before? Let me think. Probably back over here in a previous lesson on normals. Yeah, and if you don't remember, you need to go back and check it out. Because what we have here, we have divide by 2 and then add 5. Well, let's see here, and that'd be 2 X, Y, and Z color, or shall we say RGB, right? That's what it's looking like. So our vec here times 0.5, yep, divided in half, plus float 3 here, and it's going to be 0.5 for what, red, which is X, 0.5 for Y, which is green, and then 0.5 for Z, which is blue. So there we are, red, green, blue, X, Y, Z. And that converts our vectors here for our normals into what? Yep, into pixels. They'll be displayed, which gives us this. Gives us our normalized textures. Now, these formulas are used for doing that conversion. Mind you, it's not necessarily going to be that way. In fact, you actually use it for view too, by the way, to translate the view vectors also. Kind of important. These are normalized, so you can get away with this. This is only going to really work with normalized vectors, though. Mind you, be aware of that. This is not going to work for non-normalized vectors. It's only going to work for normalized ones. So yes, you can use it for multiple things, but they have to be normalized vectors, because otherwise, if you have the magnitude go well outside the range of, well, this only works in the range of what, -1 to 1, right? So anything outside that range, it's not going to work. So it has to be a normalized unit vector, of course. All right, so float 3 here, texture 2 vector. Open parentheses, float 3 here, text, close parentheses, open curly brace, return. And what we have here, we have text minus float 3, and what we're doing, 0.5, comma 0.5, comma 0.5, close parentheses times 2. Now, we've seen that before, haven't we? Yep, back over here, we sure have. So where did we see that one at? Oh, look at that. Here it is. 0.5 subtracted throughout, and then what we did, we multiplied it times 2 afterwards. That is what we did to make it work. Alright, so that's what we have going on here. So our texture here is -5, -5, -5 for RGB or XYZ, however you want to put it, times 2O afterwards, and that converts it back from a pixel, the range of 0 to 1, back over to a vector of range of -1 to 1. And if you don't remember how this works, please go back and check out your normal theory video, because that is very important. Not to mention just for normals, but also again is being used for other things too, like for instance this view. So very important. All right. Now we're going to create our multiple render targets, or MRTs, as it's called, for deferred shading. Alright, so this is the pre-method. We're going to do this before we actually combine these textures. So we need to output these textures. And at this pre-step here for handling our MRT for multiple render targets, for combining them for our PS shader here, we need to generate them first. And this is what generates our MRTs. You could call it generate MRTs, PS, if you want, or something like that. Alright, now something I found out the hard way, by the way. So I called this here, first off, let's go over this here. Void pre-MRT underscore PS, open parentheses, VS out, space, IN, comma. Now we're used to seeing this, except for the comma part. Then you need to add this here. And the reason why I was like, oh, well, I'll just throw this into a struct, right? And then I'll out, and then just do it all in one out, right? Nope, not happening. Can't do it. Doesn't allow it to be inside of a struct. You have to have multiple outs being passed in here through this function, and it passes in, I believe, as a relative reference variable or something along those lines, with a pointer happening inside of the 3D card's memory. And so it points to the actual memory addresses, and that way when a value is changed in this thing, it's actually changing it inside the function here, it's actually changing it in the memory directly, so it can be accessed outside of it, and then it's not destroyed afterwards. So it's kind of like a C++ static variable in a function with a returned value, something like that. Or if you want to say relative reference being passed in with the ampersand sign in C++, would be what it's like. So if you're familiar with C++, that's just making sense of what I'm saying. If you're not, that's going to be totally confusing. Basically, what I'm saying is we are creating this variable here that we are passing the address, the actual physical address, and we're not passing the data here instead. We're actually passing the address to it. And then the data is being assigned to that memory because we know where it is in memory and the address. And then when it gets passed back from this function, it's nothing to really pass back. It's already assigned the actual data to the actual memory location. So when you just access these variables outside of the function, it just works. And that's kind of what's happened. So it's really quite pretty, and it's really quite nice, and it's really quite seamless, and it's awesome. But I believe that's what's happening underneath the hood. Now the cool part about this is that that's why you don't see a return statement. There's no return statement here because it is being passed a relative reference variable here for our yeah. We just don't have to tell it that. It kind of knows it when we set this out here. So out here, float 4 here, color out. Can't use color because colors are already a reserved name. Colon, I tried it. Color 0, comma, it gave me an error. Out here, float 4, normal out here, colon, color 1, comma, out, float 4 here, view out, colon, color 2, close parentheses, and I can use these now inside of here. Works for me. But this way we have multiple color outs, and so we actually have to denote them by their numbers. And this is multiple textures going out to the G buffers, and that's literally what's happening here. Is actually going to render out to the G buffer. Works fine for me. You know, it'll be fine. It'll work out great. So normal out equals here float 4 here. Yep, float 4. Open parentheses vector to texture here. So we're going to convert our vectors to our textures mathematically. We're going to normalize our in.nwn, right? Before we're passing it in here, because again, it needs to be normalized if we're using this function, right? Because it only takes the range of vectors that are normalized. So that's what we're doing with our normals that are in world space coordinates that have been normalized. We're normalizing them anyways. All right, comma here, 1.0 to make it a homogeneous coordinate system, and it's getting returned back here as a float 4. Now, think about this, it's getting converted to what? Pixels. So what does 1.0 mean? 1.0 means alpha. It means it's not going to be seen otherwise. So all this other space around here is going to actually become transparent. So it's important to realize that. All right. I ran this on another computer, and it's actually transparent in here instead of black here for the background, which is quite interesting. It's showing up as black. But on another computer I did this on, it actually came up transparent here in the background instead of black. So be aware, yeah, we actually are setting in the opacity of full color with no transparency on our on our images, and that's important to be aware of that. Alright, so view out equals float 4 here, open parentheses, vector to texture again, so we're doing another vector to texture. We're going to have to normalize it first though for what we're passing in. So in this case what we're passing in is in.vwn, which is the view vector here in world space coordinates. It's been normalized. Close up parentheses, close parentheses again, right, for our normalize, and then we're going to do what? We're going to set our alpha to 1, so it's solid color here for our homogeneous coordinate system, and we're passing that out to view out. Now we're going to generate, and so that was the view out one there. This one here is our normal one there. Now we need to generate what one? Our color one. Yeah, color sounds great. So color out equals float 4 here, open parentheses, KD times text 2D here, open parentheses, color sampler, comma, in.uv, close parentheses, .rgb, comma, 1.0, again, setting our solid alpha here, close parentheses, semicolon. Okay, what was that? Well, remember KD is our actual, what? It's our texture value. Yep, sure is. So this matters. What happens if I come in here? Whoa. Yep, that's what the KD does, right? Awesome. Now, what does this 2D color sampler do? Well, that's this texture here. We're assigning this texture with this color, and we're multiplying them together, all right? And we're returning 1.0 for alpha, so that way it's solid color everywhere where there should be texture and lighting. And then, you know, alpha 0 or black or whatever it is going to be for everything else in this around it. So very cool. So it generated all three of those images. Awesome. Okay. Let's look at some more stuff. All right, I'm just going to stop right here at this point. Now allow people to have time to copy this down while I go over to this next part here. And this is FS out here. And this is the main PS now. So after we're done running this function here, we're going to run this one here for our PS. And a whole nother pass though, mind you. So of course we'll have to run the vertex aligned quads before we can actually run this function for doing the rendering processing on it. Okay, so FS out here, main PS here, open parentheses, VS out, IN, close parentheses, open curly brace. FS out here, out, semicolon, float 3, in, which is our in normalized here, texture to vector. So what are we doing? We're taking our pixels from our image here, right, because we outputted them earlier, and we're going to convert them back into a vector. Very cool. And that's what we're doing here. So here's our normal one. So we're taking our deferred normal sampler. That's how we're accessing it, right? So we're accessing that pixel lookup. We're saying in.uv. So we're accessing the UV lookup on it from the screen. Very cool. .xyz. So here we're getting our normal information from it. This is converting these pixels back into vectors, normal vectors. Okay, awesome. Let's do it also for the view angle too, right? So we're here, we've actually delayed our calculations of our lighting in this way. So this is deferred lighting at this point. VN here, right? Texture to vector here. Text 2D here, deferred view sampler, comma, in.uv. So what we did, we're doing our view, right? We're taking our view vectors here and we're converting them from texture pixels into actual vectors that are normalized vectors, basically, back from the image. And that's what's happening here with our view. And we're using the sampler to look up each individual pixel for each individual vector. Makes sense. And of course we're massively multi-threaded computing this. And that gives us our view normalized. LN, our LN is our light vector here, equals normalized here, open parentheses, minus lamp 0 dir, close parentheses, semicolon. Alright, so we're going to normalize the negative direction opposite of our lamp. And that's what we want, and that gives us this nice shine here on the surface. Otherwise it won't, because we go in the wrong way. Now remember, we didn't have the RN or HN previously. We'd have a reflected angle coming from the light bouncing off the surface point back to the camera calculated previously. We're going to do that now, and we're going to normalize that at this pass here after the fact. And we can do that. We can actually get away with that. So that's very cool. So let's just handle all our lighting and all our processing here for these all at once for all our objects here in one pass. So it's pretty cool. Float 3 here, HN here, equals normalize, open parentheses, VN plus LN, close parentheses, semicolon. And what we have here, we have our view vector normalized plus our light vector normalized. And we are normalize these together to get HN, or you could say RN, doesn't matter to me. But basically this means either you can say HN for the half angle, you want to call it that, or you can call it reflective vector from the light. That works too. It doesn't matter. It's all the same stuff. But anyways, it helps determine what the specular is going to be based on the angle of reflection coming back from the light to the view. Okay, so lit V here equals what? Our lit function, and it says dot here. We're going to say ln, comma nn. So we're going to say what? Our light vector here with our normal vector, both have been normalized, the dot product of them. And then we're going to do the dot product of our what? Our HN and our NN here. Very cool. And then we're also going to pass in our specular value. Okay. For its specular exponent. Awesome. Which again is defined in here, which right now is 55. But I could go in here and I could change this. As you can see, make it super shiny if I want, or whatever. It doesn't matter. It's up to me really what I want to do, or up to you. so on and so forth. Alright. Just got back to 55 because I felt like it. Okay, anyhow. And this is going to go back as you remember. Remember, x is nothing. It's just 1 That's all it is. So it's no point multiplying that through. It's a superfluous calculation that's not needed. But however, y and z of lit corresponds to both our what? Our diffuse and our specular. So yeah, they kind of matter. So we have to be aware of that. Our lit v dot y is our diffuse one, and our lit v dot z is our specular one. We need to use both for when we're doing our specular here. So we're doing ks times our lit v dot y times lit v dot z here, close parentheses, times lamp 0 color here for our directional color light. The color of our directional light. There, it's going to get multiplied, and this is going to be for our specular. So that way, when we change some things around the light, it actually colorizes our specular also. Very important aspect. Okay, very cool. And then let's look at some other stuff too here. And that's our diffuse texture here equals text 2D here, open parentheses, deferred color sampler, comma, in.uv, close parentheses, .rgb, semicolon. Let's get sent into our deferred color sampler. Alright, in.uv, RGB for that. Alright, float 3 here, diffuse equals, open parentheses, lit v dot y times lamp 0 color, close parentheses, plus Ka, close parentheses, times diffuse texture, close semicolon, as far as that goes. And then out dot color equals float 4, open parentheses, diffuse, plus specular, comma, 1.0, close parentheses, semicolon. Alrighty. So this will let us compute. So lets us compute our specular values. Terms here with the lighting and diffuse texture. This will do our diffuse texture here for a deferred color sampler. in.uv RGB. And then we have our diffuse here equals what? Lit v dot y times lamp 0 color, close parentheses, plus Ka, close parentheses, times diffuse texture, semicolon. Alright. Lit V here is going to be diffuse. Your lamp color, because that's your diffuse intensity, whatever. And then add that to your Ka versus your ambient, and then times your diffuse texture. Kind of did that earlier, I guess. So that way I don't have to worry about doing ambient down here. Although you could have done ambient down here, and that works too. Diffuse texture, semicolon, and then we're just doing out dot color equals float 4 diffuse plus specular, comma 1.0 for our for our alpha, close parentheses, semicolon, and that takes care of that. For our lighting, return out, and actually our texture, 2D texture too, being applied, as far as that goes. So that's cool. So it gives us our deferred shading and our deferred lighting both. So very cool. Return out gives us our final return. It goes to the frame buffer to be displayed on the screen. Close curly brace here. And then we're getting down to our techniques. And our techniques are 2 passes, so there's a little bit more work to this than what was previously there. Alright. I'll tell you what. Let's do like a hybrid here, where I move it just like that, just in case the people are still copying. Alright, so let's just do that right now for our technique. And I'll move it down as we go here, okay? So technique 0. Of course, now, honestly, I'm keeping it technique 0 and pass 1, pass 2, pass 0, pass 1, etc. for our different passes here. It's not really the best naming. I'm doing it simply because you're familiar to seeing it, and not because it's a good naming convention. A good naming convention on it would be like technique deferred shading, for something like that, or technique deferred shading and lighting. And a good name for it would be like, for pass 1, be like, oh, I don't know, compute MRT's pass, and then the next one would be like combine or like deferred shading and lighting, pass or something like that down here. And you could do that, that'd be fine. for those kind of things. If you're doing different particular passes down here for your different multiple rendering targets, then you could have each pass as what's basically what you're doing named out here, and that'd be ideal, especially when you start getting into this multi-pass stuff here. All right, so we're going to do a string here. Script equals here in quotes pass equals P0 semicolon close quotes, and then we're going to do the next one here in quotes here pass equals P1 semicolon close quotes semicolon close greater than sign open curly brace pass P0 here open less than sign. All right, string here script, yeah, it keeps going by the way. String here script equals what in quotes here render color target 0 equals deferred color texture semicolon close quotes. Whoa, that's a mouthful. Yeah, well, makes sense though. Our color render target, we have multiples. Remember, we have 3 of them. 1, 2, 3. So that's what the deal is with that. So we're going to say render color target, which is these right here, and we're saying 0, which is going to be the first one, which is this color one here. And we're saying it's equal to what? Deferred color texture. Well, that's the one we set up above for our annotations for our texture with our sampler too. So this is the actual texture one. So we're saying that target goes to that texture. So that way when we say out color out there, and we're outputting it for all 3 of those, color out, view out, and normal out, they're actually going to their respective textures. If we didn't say this, it wouldn't. So it's important to do this. So render color target here 1 equals deferred normal texture semicolon close quotes. Render color target 2, it's copy and paste, man, equals deferred view texture semicolon close quotes. So after you have the first one, copy and paste these others. Bam, you'll be done in no time. And then copy and paste for the last one here and just make some changes. So render depth stencil target equals in quotes, sorry, still part of the quotes, depth buffer texture semicolon close quotes. Okay, next part here, open quotes here, clear set color equals clear color semicolon close quotes. So again, we're clearing out this background so we get black here so we don't get a muddy set of pixels that don't get updated. So we need a clearer color for every frame, absolute must. Clear set depth here equals depth here for our depth texture or whatever. We need to clear it every time. It's very important. And then clear equals color 0 semicolon close quote quotes. Open quotes clear equals color 1 semicolon close quotes. Clear equals color 2 close semicolon close quotes. Clear equals depth semicolon close quotes. Open parentheses quotes, I'm sorry, draw equals geometry semicolon close quotes semicolon for this overall thing. Because remember, this entire thing is one line of code that would be spaced by just a single space separated for each option that we're passing in. So semicolon is what's the overall terminator for this whole group. Alright, so open, we just do it in a row like this because it's way cleaner than making this line go on until forever. Alright, so close greater than sign here, and then open curly brace here, def test enabled equals true, semicolon, def mask equals true, cull face enable equals false, semicolon, blend enable equals false, semicolon, def func equals L equals, semicolon, vertex program equals compile VP40 main VS, open parentheses, close parentheses, semicolon, and then we're going to say fragment program. Now, mind you, you should be able to get away with VP30 and FP30. The fragment program equals compile FP40 here, pre MRT underscore PS, open close parentheses, semicolon. Alright, so I'm going to scroll this down some. Alright, and see if I can't prove that being compatible with FP30 and 40. I don't know if I want to try it beyond. Oh, no, it's not. 40 it is. That's always great to find out, right? Okay, so yeah, FP40 and VP40 seem to be very important. So make sure you keep it at that, because you can't go below that right now. Wow. Alright. Awesomeness. I'm going to scroll down a bit more. My apologies. Feel free to copy and paste this up here, and then paste it down here and say pass 1 instead of pass 0. And then we'll just type this up. So it'll save you a lot of typing. And then delete whatever is in your target, and let's leave that semicolon afterwards for target 0, 1, and 2. So you have nothing in response to those. Same thing for your rendered depth stencil target. Now, you're not going to do that anymore because you've already rendered it out in the other pass. So there's no need to render this. So you're going to leave these blank, okay? That's why we're leaving them blank. And you're doing a string script equals here, of course. The pass here, P1, or say it, open lesson sign, but you should already have that from the copy and paste. Alright, so clear set color equals, clear color is going to be what? Black. Semicolon, close quotes. Open quotes here, set depth here equals clear depth, semicolon, close quotes. That's also important. So remember, we need to clear our depth, we need to clear our color because we're doing another pass here within the same frame. Open parentheses here, clear equals color, close, semicolon, close quotes. Opening quotes here, clear equals depth, close, semicolon, close quotes. Open quotes here, draw equals buffer, semicolon, close quotes, semicolon. Close greater than sign, open curly brace, depth test enable equals false. Now note, it is true here for depth test enable and depth mask. That's important because we're dealing with depth here up above when we're first calculating this. We are not dealing with it when we're talking about rendering straight to the screen because we're off of these textures we've already computed. So there's no need to have depth on the ones down below here. So depth test enable here is going to be false. And you'll notice this is draw geometry here. This is draw buffer because we're going to our frame buffer, and this is screen space technique here. So be aware of that. We're going to the buffer. Alright. Cull face enabled equals false, semicolon. Blend enabled equals false, semicolon. Def func equals L equals, semicolon. Our vertex program equals compile FP40 screen VS, open close parentheses, semicolon. Fragment program equals compile FP40 main PS, open close parentheses, semicolon, close curly brace, close curly brace, and we are done with that shader. Once you are done, you should be able to drag and drop this into the scene, and you should see this result here. Now, if you want to unapply a screen space shader, and I have one of my students show me this, he found, and it's really made life a lot easier than having to hit the Control Z to undo. If you come in here and you go to your evaluate here, you can actually delete your evaluate. So that can actually remove your screen space shader without having to undo and lose a bunch of shaders in the process. I'll show you that real quick. See, and that removes our deferred shading. I can just come back here easily later on, however, and then reapply it by dragging and dropping it. So if you need to remove it, that's how you do it if it's not working for you. This is how you can remove it to try another technique or whatever. Or if it is working for you, it doesn't matter. You still need to remove it. That's where you remove it. Alright, but this should be able to, you should be able to get this working. Mine works fine. So if it doesn't work for you, then you got a typo somewhere. As it stands, though, we have 391 lines. I was off earlier about how long this program is. So yes, almost 400 lines of code for this. So this is a more advanced technique. It did take a good bit more work to get this working in the pipeline, but it's very cool once you get it going, and it does allow for some really nice speed increases. There are some issues with it, but those can be worked around. This, it would be, as you can start to see, should really be applied into an actual game engine, and it's great for learning purposes and testing purposes doing FX Composer, but doing anything really extensive, I think it would be kind of difficult to do in FX Composer. Don't get me wrong, you could do it, it's just would be easier, I think, maybe to possibly implement it in the actual game engine, because you're dealing with, you don't have full control over FX Composer like you do an actual game engine, where you can just get in there and code whatever you need to have done wherever and whenever you want. But at this point, we've pretty much gone over a good portion of what you can do with the architecture inside FX Composer. It's really quite powerful and very flexible and very capable. But there's still times where there's things where you just need to do it, and you really can't do it easily. And this lets you, and in the game engine, you really have that extra freedom to do what you need to do. So please be aware of that and remember that. So if you start on the really advanced, crazy stuff here, at some point in time, you will need to go to a game engine and implement this, as it's not possible to do everything you could imagine in FX Composer. It's a very nice program, but it has its limitations, of course, because it would have to. I can't imagine writing a program I mean, it's amazing the amount of functionality and capabilities and what you can do with FX Composer as it is right now. You know, as far as that goes, the techniques here, as far as what you can get away with, and the fact that you can do pre-pass and post and actual geometry, and then how you can manipulate it and control the system as far as that goes for where you want and order the functionality. Man, that's pretty impressive that FX Composer could handle all that. It's really, really quite cool. You know, but you know, for other techniques, like we can't even get into it, require like tessellation shaders or geometry shaders. You can't do that in FX Composer 2.5 at all. You'd have to implement that in your own game engine. So there's some things that just physically aren't possible to do in this program at this time. So, of course, though, when you're watching this video, they may have come out with a new version of FX Composer that does allow you to do some of that stuff. So, but at the time it's recording this video, you can't do that stuff. So, there we are. But basically, there's deferred shading with multiple render targets. It's quite cool, and deferred lighting too, mind you. And it's very powerful and can really help speed up things. And you can take advantage of those speed ups. But with that, it's going to let us open up to doing some other more advanced techniques that we couldn't really do otherwise until we got into doing some deferred lighting, so that we could take full advantages of that for shadows and some of that stuff. So it does make life easier because we can actually do some techniques, and that is one of the wonderful things about it. It does simplify your pipeline process here. So very powerful and very cool. It does have some trickiness to it, but you know, all that can be overcome. So with that, my name is Nate Nessler, and this has been Hyperactive Studios, and thank you very much.